Hi, I'm Zhou Han from the University of Tennessee, Knoxville, and I'm glad to share about our paper, Byzantine-robust Federated Learning through Spatial-temporal Analysis of Local Model Updates. This is a joint work with Dr. Liu from Google Research, Dr. Zhang from Oak Ridge National Lab, and my advisor, Professor Liu. Federated learning is a distributed learning framework that allows multiple clients to collaboratively train a machine learning model under the coordination of a central server, while keeping their private training data locally on the device without being shared or revealed to the server or other clients. Federated learning can be conducted among a small set of reliable clients or among a large number of mobile and edge computing devices. The strong privacy guarantee of federated learning makes it extremely attractive in areas like mobile computing and telemedicine, where it has enabled a broad spectrum of real-world applications, such as next word prediction in Google Gboard and collaborative learning of diagnosis model between multiple medical institutes. At each communication round, the following three steps are performed to achieve the federated learning objective. First, the central server broadcasts the latest global model to all the clients or a subset of clients that are selected to participate in the round of training. Second, each client computes an update of the model on its local dataset by performing several iterations of gradient descent. Third, the server updates the global model by aggregating the local updates according to a certain aggregation rule. Federated averaging is the most widely used aggregation rule for communication-efficient federated learning, which aggregates the client's updates by computing a weighted average. However, federated averaging is not fault-tolerant, and even a single faulty or malicious client can prevent the global model from converging. To address this, several theoretical approaches based on gradient similarity or robust statistics, such as Chrome, median, and trimmed mean, has been proposed to achieve Byzantine resilient learning. Although offering provable guarantees, in practice, this method only provides a weak level of tolerance to attacks, and the resulting models could still be influenced by malicious clients. Other methods attempt to detect and remove malicious clients by estimating each client's reliability through calculating the descendant of the loss function, or projecting the client's updates onto a latent space using a variational autoencoder. To defeat time-coupled attacks, existing methods relying on historical data has been proposed to adaptively estimate the quality of clients' updates using a hidden Markov model. However, this method either requires prior knowledge on the client's data distribution for loss descendant estimation or autoencoder training, which is hard to satisfy in practice, or require the server to keep track of the mapping between the submitted updates and the client's identities, which may lead to severe risks of privacy breaches. In this work, we aim to design an aggregation scheme that can tolerate attacks or failures in a more dynamic federated learning scenario while achieving privacy preservation without requiring prior knowledge on the number of faulty or malicious clients, the distribution of the client's data, or the mapping between the submitted model updates and the client's identities. To achieve this, our algorithm inspects the client's updates from two critical perspectives. First is the spatial perspective, where we leverage geometric patterns to filter out malicious updates within each round of communication. And second is the temporal perspective, where we utilize historical data from previous communication rounds to detect temporal outliers. We first perform a preliminary study to compare the distributions of the model updates computed by the benign clients and the updates from malicious clients. We visualize the updates selected from an arbitrary communication round in a two-dimensional space, and we observe that these malicious updates diverge from benign updates, causing the aggregated global updates to be biased and deviate from the direction of the true gradient. Based on this observation, we adopt a clustering-based method to filter out these malicious updates. Specifically, at each communication round, we first compute the pairwise cosine similarity between the updates to construct the affinity matrix. And then we apply a clustering algorithm to produce two candidate clusters. Finally, we select the majority cluster as a benign cluster based on the assumption that the majority of clients are not faulty or malicious. Due to the time-varying behavior of clients, solely relying on spatial patterns is insufficient, especially when facing a sudden violent perturbation. To cope with these time-varying behaviors and achieve temporal robustness, we propose to assess the quality of the aggregated updates by comparing it with a speculated value of update that is predicted according to historical statistics. The intuition is that if the current update significantly deviates from previous results, this can indicate an abrupt change in the state of the participating clients. Specifically, we first compute the momentum of the gradients using its exponential moving average, and then obtain the cosine similarity between the gradient and its average. Finally, we update the global model according to the adaptively adjusted learning rate. We consider both cross-silo and cross-device federated learning scenarios for our experiments. In each scenario, we compare our proposed method with the standard federated averaging and three representative baseline methods, namely chrome, median, and trimmed mean. We consider the normal setting and three other faulty or malicious settings in each federated learning scenario. In addition, we consider two state-of-the-art time-coupled attacks that can circumvent existing Byzantine aggregation rules by accumulating small perturbations over many training runs. From our experiment results, we observed that on all four considered datasets, the proposed method can achieve a convergence speed that is comparable to baseline methods in the normal setting, and also remain robust in all three faulty and attack settings. Although the baseline methods are able to achieve satisfactory performance in the Byzantine and noisy settings, they fail to resist the stronger label flipping attack. In the cross-device scenario, we observed that due to the varying number of malicious clients being selected at each run, the test errors of all methods become highly variable between consecutive communication runs. However, the proposed method is still able to obtain a stabilized gradients and provide enhanced robustness. Most noticeably, in the case of Cypher-10 dataset, we can achieve the lowest test error against the label flipping attack that is comparable to the performance when there is no attack, while all other methods cannot converge at all. In the case of time-coupled attack, we observe that the IPM attack is able to completely break the chrome aggregation rule on the MNIST dataset, while also causing a negative impact on the convergence of other aggregation rules. On the Cypher-10 dataset, the IPM attack causes the final test errors of baseline methods to be increased by 3 to 18%. The ALIE attack is found to be extremely effective against chrome and trimmed mean on both datasets, leading to complete modal divergence. Our method, on the other hand, is able to resist those time-coupled attacks on both datasets, achieving lowest test errors that are closest to the ones produced by federated averaging, with no attack across all settings. For more information, please refer to our paper. Thank you for listening.